So thank you, Geoffroy. So good morning, everyone. First of all, I would like to thank the organizers, especially Romain, for the kind invitation. It's a long time I haven't been in cargèse, actually. So in this lecture, I will try to give you a pedestrian introduction to Anderson localization. So I know that many of you are actually specialists of classical wave scattering, classical wave imaging in optics or acoustics of complex media. But here I deliberately choose to focus the discussion on localization of matter waves, essentially cold atoms. And this is actually for two main reasons. So the first reason is I think that especially in this community, I always thought it was extremely useful to know a little bit what's being done with other people's waves, I would say. This allows you to get some new ideas sometimes and also to see, so this is more from the experimental point of view, but to see what can be done, what is possible to do, what is not possible to do with your setup as compared to others. So the second reason is more fundamental because it turned out that in quantum physics nowadays, AMO systems and in particular cold atom platforms are seen as genuine quantum simulators, which means that with these systems have reached today a level of technicity and precision such that with them you can really design and control textbook Hamiltonians, and in particular disordered Hamiltonians. So here in this talk I will try to give you a couple of examples of this in the context of disordered systems. But of course the field of quantum simulations is much broader nowadays, and if you are interested I can only invite you to look at this book which was recently edited in French and in English, and in there you have really plenty of illustrations of let's say quantum technologies with cold atoms by many talented groups in France. We have written in this group a small chapter which is especially dedicated to cold atoms in disorder with my colleague here, Vincent Josse from Institut d'Optics, who actually made a lot of experiments that I will present today. Right, so now before getting into the business of localization, let me first introduce the basic problem we are interested in. So this problem is pretty simple. It's the propagation of a quantum particle. So for your purpose, you can see it as a wave, but for my purpose, I will often call it a quantum particle with a certain momentum k in a disordered potential V of r. And the question I will address during the talk is what's the motion of this particle at macroscopic scales, typically scales much larger than the wavelength, the de Broglie wavelength. In passing, notice that here I illustrate, in this illustration, the disorder is modeled by continuous function of the space coordinate. And this is because actually in many cold atom experiments, this is the relevant model of disorder. In many experiments, very often the disorder is created with continuous optical speckle fields for the atoms. By exploiting the light-atom dipolar interaction. Right, so now to illustrate what this macroscopic motion may look like, let me first show you the result of this cold atom experiment from 2010 from Institut d'Optique in the group of Thomas Bourdelle. So what they did here was to confine a cold atomic gas in a 2D plane using lasers, okay? And then they studied the time evolution, the time spreading of this gas, of this cold gas in the 2D plane by further subjecting it to, to a speckle potential here. So what you see here is a fluorescence image of the Bose gas, of the cold atomic gas in 2 dimensions. And below you have two spatial cuts of the density distributions at a given time. So this is at a given time, and the blue here is in the presence of the speckle field. The red is in the absence of the speckle field. And so you see that obviously when the disorder is present, the spreading, the expansion is slower. So now they also looked at the density at the cloud center, okay, at the maximum of the density as a function of time, and they identified a very clear one-over-time decrease, which in two dimensions is a characteristic signature of diffusion process, a diffusive expansion. In particular, it should be contrasted with the 1/t square expansion that you get in, let's say, quantum mechanics lectures for the problem of wave packet spreading in free space. So in other words here, everything goes, if you wish, as if the atoms were behaving somewhat classically and were undergoing classical multiple scattering random walk, effective random walk, at least through the fluctuations of this potential. So now from a theoretical point of view, to describe this classical multiple scattering, the appropriate treatment is provided by the Boltzmann equation. So I remind you that the Boltzmann equation is just a partial differential equation that tells you how the probability density to find a certain classical particle at a point rk in phase space evolves in time, given that it is subjected to collision processes. So these collisions are usually described by a term here in the right-hand side, which is called the collision integral. And physically, it's just the rate of change of the phase space distribution due to collisions. So what are these collisions? Here, well, it's just scattering events on the disorder potential. So the collision integral for this specific problem takes the following form, which looks like a Fermi golden rule. So you have a matrix element here, which gives you the probability for a particle with the momentum k to be scattered in another direction, k prime, on the disorder. Then you have this difference in populations of the two phase space distribution in the in and out channel. Okay, so if you have no particle in the K mode, then nothing is scattered, obviously. And then you have this delta function, which tells you that scattering is elastic. And finally, you integrate over all possible outgoing momenta. So in general, this Boltzmann equation must be solved numerically, and as a matter of fact, many of you probably did it already, because this, in the context of classical wave scattering, is just the radiative transfer equation. Right, so this must be solved numerically in general, but if we are essentially interested in the limit of long times, then it can be simplified. It can be simplified because at long times you have many scattering events, so the direction of the momentum is almost randomized by the multiple scattering process. Therefore, the phase space distribution becomes nearly isotropic in K, and if it's nearly isotropic, you can decompose it in its first spherical harmonics, let's say, at long times. And then by inserting this truncation scheme into the Boltzmann equation, you end up with the well-known diffusion equation for the particle density, okay, at a given energy or a given momentum K. So this diffusion equation defines the diffusion constant, which is a function of the particle velocity v, a function of the dimension d, and it depends on a fundamental time scale, tau, which is called the transport mean free path, and the transport mean free path is just precisely the time scale beyond which the momentum is randomized by definition. Okay, so this is the diffusion equation that you get at long time. And now if you come back to the previous cold atom experiments I presented, in that experiment you have a wave packet spreading in a, let's say, infinitely large disordered potential. There are no boundaries anywhere. And so the relevant solution of the diffusion equation is just the Gaussian kernel, the diffusive kernel. And pay attention to the density at the cloud center at r equals 0. It decays as 1 over t in 2 dimensions. Okay, so that was observed, that's what was observed in this experiment. So also relevant in certain experiments is the in and out configuration. So this configuration in quantum physics has been historically explored a lot in the context of mesoscopic physics of electrons, where people were interested in just looking at the transport of electrons through mesoscopic disordered conductors or wires or films. But obviously, this geometry is also extremely popular in your community, where you have a sample, you want to characterize this sample, the sample is possibly disordered, then you have no choice but sending a wave through the sample and looking at reflection or transmission. So this is what is relevant here. We would like to compute the transmission coefficient of a certain region of space, a disordered region of space of length L and diameter W for a given quantum particle with momentum K. So if we model this with the diffusion equation, the difference compared to previously is that now we have boundaries. So if we have boundaries, we need to complement the diffusion equation with boundary conditions. So these boundary conditions, in general, they depend on the specific setup you are looking at. So if you think of an experiment of mesoscopic physics with electrons through a sample, usually in this field you have a mesoscopic wire and then it's connected to big electron reservoirs, which means that if when the electrons leave the sample of interest, then they go into the reservoir and in good approximation they never come back. So you can use Dirichlet boundary conditions, but of course, in different contexts, you could use different boundary conditions with no change on the results I will show you in a second. So the important point is that when you have boundaries, in general, the solution of the diffusion equation takes the form of an eigenmode expansion, like this. And for this specific case, if you look at the current density here, at the output interface, and you sum over all possible directions, meaning you or you sum over all the transverse sections, so you take the momentum 0 here, you obtain the total transmission coefficient of this particle. And the result is just a ratio of 2 length scale, the mean free path divided by the sample length. Okay, so this is a characteristic feature of diffusive transport through a disordered region. I will very often in the rest of the lecture not work with the transmission coefficient but with another object which is called the dimensionless conductance. And for this particular waveguide geometry, the dimensionless conductance is essentially the transmission multiplied by capital N, the number of propagating transverse modes in the guide. And this number is proportional to the cross-section of the guide. And the interest of this relation and of this conductance is that you can easily formally generalize it to any dimension. So that's a waveguide geometry. It's called a quasi-1D geometry technically. But you can generalize it formally to any dimension by substituting for the cross-section the thickness to the d-2, in which case you obtain a very well-known relation for the dimensionless conductance of diffusive conducting systems. This is sometimes called the Ohm's law. What is important here is the algebraic dependence on the sample size, which is a characteristic signature of diffusion. Now, of course, there have been plenty of experimental measurements of classical wave scattering through diffusive media, and all of you know this much better than I do. But here I would like to focus on something else. So an experiment which, in my opinion, is really an exceptional experiment in AMO physics. So it was carried out in the group of Thielmann-Esslinger in Zurich already 12 years ago. And what they did here, so this experiment was actually designed to quantum simulate an experiment of mesoscopic physics with electrons, but with atoms here instead of electrons. So what they did, they took a gas, a cold gas, a Fermi quantum gas actually, and using a laser, the Lagergos mode of a laser, I think, they managed to really sculpt in the gas a narrow constriction here, a narrow constriction connected with two big atomic reservoirs, okay? So they really sculpted with light somehow a mesoscopic physics sample. And then they created a small atomic imbalance between these two reservoirs, so to induce a current of atoms through the construction. And by measuring this current versus the population imbalance in the two reservoirs, they could access this dimensionless conductance. So in this specific example, they actually probed the diffusive conductance because in addition, it's not shown here, but they superimposed on top of the construction a small speckle beam to also simulate optically the disorder. And in that case, they could in particular found this proportionality with the cross-section here of the construction. But even beyond this, the measurement of this conductance, which is a global measurement, they could also achieve spatially resolved measurements of the resistivity inside the constriction using an atomic microscope, which at the time, so this was really cutting-edge technology. And here you see an example of such measurement of resistivity really in the constriction at all positions for a diffusive constriction, so with the speckle where the resistivity is finite, so it should be constant, it's a bit fluctuating, and also for ballistic constriction with no disorder, in which case the resistivity is zero. The conductance is infinite because you have perfect transport. So this is an example. You have so there are many other things in this experiment that I will not discuss. In particular, the fact that you have this huge increase of the resistivity you see at the two sides of the constriction. This is actually a manifestation of an effect which is called the contact conductance of the constriction. So these introductory considerations eventually bring me to the outline of the talk, of the rest of the talk. So in the first part, I will give you a crash course on Anderson localization. And to do so, I will actually revisit the problem of transmission, but in 1D, in one dimension where diffusion clearly not works, it's replaced by Anderson localization. So this will allow me to introduce basic concepts like the Thouless criterion and the single parameter scaling of the conductance. And finally, I will say a few words about the Anderson transition. Then in the second part, I will address the dynamics of localization because in cold atoms experiment, this is actually what people do. They do dynamical experiment. And at the outset, I already showed you an example, an illustration of this. And finally, in the remaining time, I will present briefly what I think is an original signature of Anderson localization, which goes a little bit off the beaten tracks. It's called the quantum boomerang effect, and it was so it's an effect that was recently measured also experimentally with cold atoms, only with cold atoms. Okay, so now basics on Anderson localization. So I thought a little bit, and in fact, one of the simplest model for localization that you can find is probably the 1D disordered Kronig-Penney model. So this model is pretty simple. It consists of a series of barriers. which are placed on a line segment of length L with random separations. So the randomness, the disorder is in the random separations. And here the goal is to compute the transmission coefficient, again of a certain quantum particle through this system, averaged over disorder realizations. And here the averaging is by definition an averaging over all these random spacings. Okay? So to do so, I will only make two assumptions. First, I will focus on the limit of very narrow barriers, so of a width much smaller than the wavelength. And this is essentially for simplicity. Second, I will assume that the disorder is dilute, meaning that the average separation between the barrier is much larger than the wavelength. So in fact, this is a condition of weak disorder, which is not necessary to do here, but the calculations and the universality of the results is much more pronounced in this limit. Okay, so to understand a bit more in detail what's going on in this system, let me first consider two barriers. So if you have two barriers, you have a Fabry-Perot, and therefore the transmission, the amplitude transmission is just obtained by summing all possible interference reflection processes inside the cavity. Okay, so this sum is an algebraic series, and it gives you the well-known Fabry-Perot formula. Observe that here the barrier separation D1 is contained in this phase here, which is just the phase accumulated on a return trip inside the cavity. Okay. So now, if you look at this formula, you can immediately see why the generalization to n barrier is going to be very difficult. Indeed, if you have more than two barriers, typically the number of interference processes, reflection processes that you need to count becomes much higher. Actually, the interference proliferate. Actually, the interference to be counted grow exponentially with the number of barriers. So this means that not only is it difficult to generalize the Fabry-Perot formula to n barriers, but even if you manage to do it, then the average over disorder will be probably extremely difficult, because this disorder appears already for two barriers in a denominator. So the trick here, and this is really the essential idea to bypass this issue, is to forget about the wish to compute the average transmission, at least for this particular example, and to look at a different quantity, which is the logarithm of the transmission. Why? Because the logarithm of the transmission is much simpler. Already here you see that it looks like an almost additive quantity with respect to the individual transmissions of the two barriers. Of course, there is still this interference contribution, but it appears through a sum here and not in a denominator like this. Okay? All right, so now let's do this. Let's compute instead the average of the log transmission. So the average, I remind you, is by definition an average over all the random phases, so all the separations. And in the first step, we can easily perform the partial average here over θ1, over this first phase in the following way. You just take this whole system and you look at it at a kind of generalized Fabry-Perot, which would consist of the first barrier, coupled to a composite scatterer that is formed by all the other barriers. So then, if you do so, you can use the Fabry-Perot formula for this composite system. And the sum over θ1, the average over θ1, just runs over this third interference contribution. Okay? Then, the point is, of course, this average in general is complicated, except in the limit of dilute disorder, which I assumed before. For dilute disorder, the phase is Kd. Kd is assumed to be much larger than 1, so D is the average separation. So it means that typically from one disorder realization to another, this phase fluctuates much compared to 2 pi. So if they fluctuate much, you can replace this averaged over theta 1 by a uniform integral over theta 1. So you have the integral of log 1 plus or minus something smaller than 1. You integrate over 0 to pi, and the result is 0. And it's 0, I would say, whatever the other phases here which are hidden in this composite scatterer and hidden in this RC coefficient. So it means that with this partial averaging over theta 1, we have actually identified an iterative, an additive relation in the problem. And you see how it works next. So we will again decompose this composite scatterer into a new Fabry-Perot, average over the phase theta 1, and proceed like this successively until the result. So at the next stage, you take the composite scatterer C, you decompose it as a new Fabry-Perot consisting of the second barrier plus a composite scatterer C prime. Here you have the barriers from 3 to n. You average now over theta 2. And this averaging cancels the new interference terms coming out, and now the log t average over theta 1, theta 2 is log t1 plus log t2 plus log tc prime, and so on and so forth. After averaging over all the random phases, you get the simple result that the average log transmission is just the sum of the log of all the individual transmissions. For simplicity, we can assume that all the barriers are the same, are identical, and you immediately come to the result that the average log transmission is extensive, okay, with the system size. In other words, the effective transmission of the problem obtained by taking the exponential of this decays exponentially with the system size. And this exponential decay is due to this proliferation of interference. So that's here a manifestation of Anderson localization. You send a quantum particle, you have a proliferation of interference, and the transmission is not at all given by diffusion. It's exponentially decaying with the sample size. So two comments, quick comments here. I don't have to say much about it, but here the localization length is the length scale over which you have this decay. So this localization, it's possible to show in this system and actually in many 1D systems in general, that it's a couple of mean free paths. So here it can be shown using a Kubo formula, but I won't do it here. The second remark is that this object here in literature is usually called the typical conductance. Actually, it's the distribution T has a certain, the transmission has a certain distribution, and this object, the exponential of the average of log T, is actually the most probable value of the transmission that you get from this distribution. So this is actually the relevant object if you do a measurement in a system, and actually if you average very little, you will obtain this, you will find this exponential decay. So the vanishing of transmission through 1D disordered systems has been observed in many experimental systems. Here I will give you just two examples. So the first example is taken from the condensed matter physics literature. So it's an old experiment of electron conduction in one-dimensional wires, disordered wires. So here you see resistance measurements in disordered wires as a function of temperature. So what happens here is that at high temperature, in fact, the electrons are coupled to the lattice vibrations of the crystal, the phonons, if you wish, and so the electron coherence is very poor. Okay, it's a very incoherent wave, and since it's very poor, the localization effect, the interference are suppressed. That's why you have a finite resistance. But as you decrease the temperature, the coherence of the electrons is restored, and you have this growth of the resistance in the limit of zero temperature. So if you wish, zero conductance. This is a manifestation of an insulator, so this is due to Anderson localization in this 1D wire. The second example is a famous experiment by Berry and Klein in optics. this time, where they could actually measure localization of photons transmitted through this stack of nearly transparent plastic films. So this is a direct realization of this Fabry-Perot, this chronic Penne disordered model. And here, unlike this electron experiment where you cannot easily control the system size, here they could directly observe this exponential decay of the transmission versus system size. Notice here that the classical prediction from diffusion is completely off. Okay, right. So now to continue to characterize a little bit more in detail this localization. From now on, I will work with a different object that I introduced before, the dimensionless conductance. So in 1D, the dimensionless conductance is very simple. It's just the ratio of the transmission to reflection coefficients. In fact, this object is much more interesting than the transmission, because the transmission is a quantity which varies between 0 and 1. But the dimensionless conductance varies between 0 and infinity. Precisely, it has two asymptotic regimes. So if your sample size is well beyond the localization length, then the reflection coefficient is close to 1, so G is close to T, it decays exponentially. You have an insulator, according to what we demonstrated before. On the other hand, if L is smaller than Xi, then the system is nearly transparent, the reflection is close to 0, transmission is close to 1, and the dimensionless conductance is very large compared to 1. So we have a conductor, if you wish. And so you see here that the onset of Anderson localization for this particular example in 1D occurs when the dimensionless conductance is around 1. And this condition is actually the very general criterion for Anderson localization, which is due to Thouless in the 70s. It's nowadays called the Thouless criterion. It's a criterion that was actually based on spectral considerations, but which was suggested to be a good criterion for localization, not only in 1D, but in any dimension. Okay, so that's what I will suppose from now. A second interesting property of the dimensionless conductance here is the scaling with the system size. So let me show you this. So suppose you have a disordered system and you decide to scale it up. So namely, you increase the size by a certain dilation factor B to have a bigger system. Then from this formula, which is exact in 1D, you can easily see that the conductance of the rescaled system can be uniquely expressed in terms of the conductance of the initial system. Okay? And if you take now the limit of the continuum, so you take this B, which is 1 plus epsilon, with epsilon very small, so you do an infinitesimal rescaling, then this relation takes the form of a Gell-Mann law equation in renormalization group theory. So the Gell-Mann law equation tells you that the log derivative of G with respect to the log of the system size is a certain function beta which only depends on G. So in other words, this dimensionless conductance has the property that somehow you take a disordered system and the property of the rescaled system are just a function of the conductance. Or say it differently, from an experimental point of view, suppose you have a piece of sample, you do measurement of transport, you know the transport. If you know at the same time the beta function, then you would know the transport of this system at any size. Okay? So now this apparently innocent consideration, which here is obtained in 1D, was extended in the late 70s by Abrams and co-workers. So this is the famous Gang of Four. So what they postulated in this paper is that this property, this scaling property of the conductance was not only true in 1D, but it was true in any dimension for any system, for any disordered system. So the postulate can be written like this. They postulated that the dimensionless conductance is the only coupling parameter that determines the localization properties of a disordered system when moving to large scales. And what they did more concretely in this paper is that by inferring the shape of the beta function, and from this simple hypothesis, they managed to draw completely universal predictions for the localization properties of any disordered system in any dimension. So let us, so here I will proceed according to this historical paper. So what they did first is to infer the shape of beta. So the shape of beta, actually, I gave it before in one dimension. It's actually this function. It can be derived from this relation. But in 2D and 3D, it's not known in general. There's no prediction. However, you can infer the shape from its asymptotics simply because at large G, according to the Thouless criterion I presented before, your sample should be diffusive. And so you should have the Ohm's law for the conductance, and therefore the beta function should converge to D minus 2 at large G. It's also possible to refine this D minus 2 with the leading order corrections in 1 over G, which are called the weak localization corrections. And conversely, at small g, Thouless criterion, if g is smaller than 1, I should have localization, so the conductance should decay exponentially, and therefore beta should be proportional to log g, taking this derivative. And now, if you simply assume from these two asymptotic laws that the beta function is a continuous function, and it's also monotonous, you end up with this famous shape in dimensions 1, 2, and 3. So I remind you, in dimension 1, we know exactly the solution from the 1D problem. But in 2D and 3D, you should see this just as a sketch. Okay, it's a sketch. I just connected D minus 2 to log G. Right? So that's what they did in this paper. And now here comes the many conclusions that you can draw from this and this. So let's first look at dimension 2. So in dimension 2, you see the beta function is always negative. Okay? So if it's negative, the dimensionless decreases with the system size. In other words, you take a 2D piece of disordered system, you increase the system size. At some point, G will be below 1. Thouless criterion, the system will be localized. In other words, sufficiently large 2D system, according to this scaling theory, always localized, inevitably localized in the thermodynamic limit. And here I would like to stress that sometimes these curves are shown like an evidence, but this is, here you can really feel why this scaling theory had such a profound impact on the field of localization, because we started from a seemingly innocent observation on the behavior of the dimensionless conductance, and then assuming just a continuity and monotonicity of this beta function, we come up with the very powerful statement that all 2D disordered systems are localized. We know now that this is not completely true, but at the time, in fact, it's largely true. It's true to a large extent. So this is a very strong statement. In fact, you can do much more even with this approach. It's possible to get an estimate of the localization length in 2D. So the method is pretty simple. It involves integrating the beta function here by starting from the microscopic scales, which are somewhere here at large G, up to an intermediate scale, the localization length, where the beta function here is still closely approximated by its asymptotic form. So if you do so, it's just an integral. You integrate this beta along the flow up to psi, and by inverting, you find that the localization length in 2 dimensions grows exponentially with the product KL. KL here is a measure of the disorder strength in your sample. So here you see a bit the nuance as compared to this statement. 2D systems inevitably localize in the thermodynamic limit, but the problem is that the condition for this thermodynamic is very stringent because the sample size should be larger than xi, and xi is typically exponentially large in many samples. And this explains why, in practice, Anderson localization in 2 dimensions have been very elusive for a long time. All right, so now, of course, the most interesting configuration for localization occurs in dimension 3, because in dimension 3, the beta function changes sign, so it vanishes at a certain value, Gc of the dimensionless conductance. So this means that unless you are, your system is exactly at that point, in general, if you increase the system size, it will have the tendency to flow away from the point. Precisely, if your parameters, the parameters of your experiment are such that you are located a little bit above GC here, if you increase the size of your sample, you will eventually become extended, diffusive. Or if you're lucky, if your parameters are such that you're located a little bit below GC on this curve, then in the thermodynamic limit, your system will be localized. So in other words, here you have a kind of repulsive fixed point, which is a classic signature of a quantum phase transition. It's called the Anderson phase transition in the present context, okay, or metal insulator transition sometimes. It's also interesting to look a little bit more carefully what this GC represents in practice. So actually, if you resort to the Tauler's criterion, you know that GC should be of the order of 1 because that's the onset of localization. On the other hand, if you invoke the scale invariance, at this point you have scale invariance, so because beta is 0, so G is independent of the size of the system. Because you have scale invariance, GC should a priori coincide with the value of the conductance in a small system. In a small system, you have no interference processes in general. You have essentially the Drude conductance, which for a small system of size L is KL squared. So if you compare the two, you see that, in fact, this Anderson phase transition point coincides with the criterion KL around 1. And this is a pretty popular criterion for the Anderson transition, which is called the Joffe-Regel criterion. So very often, experimentalists who want to observe this phase transition, they try to fulfill this criterion as much as they can. Very much like we did in 2D, in 3D we can also integrate the beta function to compute localization length. So here I'm doing this a little bit fast, but the principle is simple. What you do is, again, you start from the vicinity of the critical point at a microscopic scale, and you integrate along the flow up to an intermediate scale at the localization length. And to take an approximation of the beta function in this region, you just linearize it in the vicinity of the phase transition. You replace it by its tangent. And if you do so, you extract the localization length, and you find that it diverges algebraically at the critical point. So this algebraic divergence defines a critical exponent nu. And if you play the same game and you integrate along the flow now above the critical point here, you get a similar condition for now the diffusive coefficient, because this is the diffusive regime, this is the localization regime. And you find that the diffusion coefficient vanishes now algebraically at the transition with the same critical exponent. So, of course, all these reasonings are a bit phenomenological. So the scaling theory here cannot tell you anything about the value of nu. We know it only from numerical simulations. It's approximately 1.71. So this is, I gave you this value because this is the most precise value I'm aware of. It was obtained from numerical simulations in the Anderson model by Slevin and Otsuki, who are really specialists. They spent their career in measuring this nu. So this is, I would say, rather reliable. A few words about practical tests of the scaling theory. So the beta function has been computed numerically in plenty of systems, and people have verified that the single parameter scaling works, which means you compute the beta function, you changes your parameter, and you make sure that all the points fall on a single line. Okay, that's the idea. So the first computations were done mostly in the Anderson model. So here I show you the historical calculation, which was done in 81 by McKinnon and Kramer. The solid curve here is the beta function in 1D, which is known exactly. I showed you the formula before. In 2D and 3D, these are numerical calculations. Here you have another example, which in a completely different system, which is studied by Sergei Petrov in Grenoble. So this calculation was based on a completely different model. It's a coupled dipole model that actually describes the propagation of scalar light in collections of point scatterers. But again, you see that this single parameter works for this model. And here, this is not a calculation, it's an experiment, a cold atom experiment, where they could measure the beta function in one dimension. And for the specialists, they could actually do it in two symmetry classes. So in the unitary and orthogonal symmetry classes, which means in a situation where you have or you don't have time reversal invariance. In passing, to my knowledge, this is actually the first and only experimental measurements of the beta function. For some reason, every time I asked experimentalists with real samples to measure the beta functions, they were afraid probably to realize that it doesn't work. But here, this was done in 1D. Yes? Yes, from the renormalization group point of view. No, you don't see it here. So this repulsion, okay, it's here. So it's, yes. So here you see that I draw arrows. So these arrows indicate how you move along this curve as you increase the system size. Because here beta is positive. So the derivative of G with respect to L is positive. So as you increase the system size, you go to that direction. So here you have the microscopic scales. Here you have the large scales. So as soon as you are here, if you increase the system size, you flow away. That's the meaning of repulsive points. It's a terminology taken from renormalization group. So it's a observation which is useful for the reasoning, but in practice for experiment, it's not. So yes, so you see from this couple of examples that this single parameter scaling of the conductance, this beta function, is really a sort of universal property of Anderson localization. But to conclude this section, I would like to nuance this statement by mentioning that the single parameter scaling argument of Abrams and co-workers is sometimes broken. We know that, for example, it's not true in the system called the two-dimensional disordered quantum Hall effect. It's a system where you have topological contributions that break the single parameter hypothesis. Less known is the fact that in 2D systems, it's also fails in a regime where your disorder is really extreme, which was shown in the 2000s. And also in the context of many-body quantum physics, when you deal with atoms with interactions colliding with each other in addition to the disorder, then the single parameter scaling can also be broken. Okay, so I'm done now for the crash course. Actually, I disseminated a little bit many properties that I will illustrate from now in this second part, which is about the dynamics of localization, essentially in cold atom experiments. So the problem we are interested in here is just the spreading of a quantum wave packet in a disordered potential. Okay? So here I show you the results of a numerical experiment where we have started from a Gaussian wave packet, which you don't completely see here. So it's an hour wave packet. And we have just propagating it with the time-dependent Schrödinger equation in a certain random potential. And here you see that the result that after some propagation time, the wave packet at 2 times here in black and green apparently localizes, so it freezes in time, in fact. And this is more evident here in this plot, which shows you the mean square width of the packet as a function of time. You see that it saturates at long time. So the data here are fluctuating, and this is because they correspond to a single realization of the disorder. But then if we average psi square over many disorder configuration, we get smooth results. Here you see the result for the density distribution of the packet at long enough time. It has this shape with beautiful exponential tails, okay, at a long time. So the freezing of wave packets at long time, together with the exponential shape of the density profile, these are temporal signatures of Anderson localization here in 1D. Okay, so now what about theory? In fact, when you do let's say dynamics with Anderson localization, in general, you run into problems. In fact, there are very little theories that allow you to describe the dynamics of localization. It's always extremely complicated. However, it turns out that a theory exists, and an exact theory exists in 1 dimension. So this theory was developed by a physicist called Vadim Berezinski in the 70s, so it's pretty old. So this theory is really exact, but sadly, it seems that it has been today a little bit forgotten, including by many specialists in the field. And just for the story, Berezinski was, so he was a theoretical physicist, a young theoretical physicist at the Landau Institute, and unfortunately he died very early. He died from a very difficult sickness. But during this time, he was really able to make important contributions to physics. So actually, its main contributions are more in the field of superfluidity in 2-dimensional quantum fluids. Where he really paved the way to the discovery of another phase transition, which is the Berezinski-Kosterlitz-Thouless phase transition, which was rewarded the Nobel Prize actually a few years ago. But in his last years, Berezinski were also very interested in the transport of quantum particles in disordered potentials. And then he managed to construct during this time a very powerful mathematical apparatus that is now called the Berezinski technique. So here I will not give you the details of this technique, but I just wanted to let you know that this technique exists and give you a bit the feeling. So the idea is that you take an observable of interest, for example, the average density, and you express it in terms of a Green's function correlator, where here the Green's function is the Green's function of the Schrödinger equation. So then you do what people usually do in perturbation theory. You expand the Green's function as Born series. But then in 1D, the Berezinski technique provides a strategy to exactly sum up all interference contributions, absolutely all of them, in the limit with one assumption, the limit of weak disorder. So I just show you briefly how it works. The techniques in the end is not so difficult. So you take your scattering events, you arrange, you order them on a line, and then you construct a certain multiple scattering diagram, which looks like this. And then you split these diagrams into 3 parts, which are separated by the source and the detection points. And when you have this, you use the condition of weak disorder, which allows you to identify a limited number of vertices that connects these 3 regions. And once you have identified this limited set of vertices, you can derive couple equations here for the 3 parts of the diagrams, just by connecting them in all possible ways using these elementary connectors. So once you have this evolution equation, actually you can compute plenty of observables you like, for 2 particle observables at least. So you can, for example, compute the long time limit of the density distribution of the wave packet. The result is pretty famous. It was obtained in 1975 by Gogolin, who really applied the Berezinski technique to obtain the result. You see that it's a bit more complicated than just an exponential. Okay. So here I show you for comparison the numerical simulations of wave packet spreading. So this is the shape of the wave packet at long time in 1D. I showed you before. And on top of it, the Gogolin distribution, you see it works very well. So as I said, the shape is not a pure exponential, but is close to exponential in the far terms, nevertheless. Okay. Right. So now let me say a few words about experiments. Just for the long times, this formula is just the long time limit, so there is no longer time dependence. It's just localized. But there are also predictions for the intermediate times. And I will show you examples later on. So the certainly most famous experiments measuring wave packet localization in 1D was performed in the group of Alain Aspect at Institut d'Optique in Palaiseau in 2008. So what they did here is essentially the same as in the initial experiment I showed you for diffusion, but here it's in 1D. So they just confined Bose-Einstein condensate on a line in 1 dimension with lasers, and then they subjected it to a speckle potential, and then they managed to probe in time by fluorescence imaging the density distribution at several times. And actually, they managed to follow this Bose-Einstein condensate over more than 2 seconds, almost 2 seconds. And 2 seconds is extraordinarily long for a cold atom experiment. If you look at the scale here, you see that you have 1 millimeter. So you have a Bose-Einstein condensate like this, which is extraordinarily big for a cold atom experiment. But there is one drawback in this experiment, and the drawback is that when you work with Bose-Einstein condensate, you have not what you would call in this community a monochromatic wave. In fact, you have a very broadband signal. So the Bose-Einstein condensate is a wave actually with plenty of energies. And this means that the profile that you have here actually is not just a single exponential, it's a combination of plenty of exponential distribution at different energies. The result is still an exponential, but it could be different. In fact, the direct observation of the Gogolin distribution I mentioned before in 1D was only achieved recently in 2022 in the cold atomic group of the Flamme laboratory in Lille. So here you see experiments of density distribution comparison with Gogolin distribution. It works well. Here, however, they use a rather different system. They did not subject the atoms to a random potential. Rather, they use a temporal form of disorder, which is a system called the quantum kicked rotor. So in short, what you have here, you have atoms and you subject them to blinking standing waves. Okay, so it's standing waves which is periodically off and on. And then if you do so, you kick the atoms, so you give momentum to the atoms, and therefore, if you wish, the atoms, they acquire momenta on a lattice in momentum space. Okay, they hop on a lattice in momentum space due to these kicks. And what happens is that in between these 2 points of the lattice, they undergo this kinetic phase, exponential I p square over 2m, and this p square over 2m is a pseudo-random disorder. So here, if you wish, everything goes as if you have a system which is dual compared to the specially disordered system. Here, actually, the disorder is played by the kinetic term, and the hopping is played by the kick term, and you have correspondingly somehow a random walk in momentum space rather than in position space. So this is why here in the experiment, if you look closely, you see that this is the momentum distribution that was plotted and not the spatial distribution like here. Okay? So a quick word about 2D. So in 2 dimensions, numerical simulations of wave packet spreading also confirmed the prediction of the scaling theory, namely two-dimensional wave packets do localize at long time, but some of the dynamics of localization tends to be very slow. Even if the disorder is strong, actually, it's very slow. I think it's because you have many of logarithmic corrections in 2D. In experiments, 2D localization was also measured with cold atoms in the same group in Lille. And in this experiment, which I only sketch here, they could in particular directly observe the exponential growth of the localization with the product KL, so this formula I showed you before in 2 dimensions. But of course, the most interesting dynamical scenario for localization is in 3 dimensions. So I remind you that in 3 dimensions we have a phase transition which coincides with the product KL of the order of 1. So sometimes in the cold atom community people re-express this criterion in terms of atomic energy equals to a critical energy which is called the mobility edge. So above the mobility edge you have diffusion, below you have localization for the wave packets. What is perhaps less obvious is the behavior if you are exactly at the critical point here. So if you are exactly at the critical point, there is a qualitative argument to give you the nature of the dynamics here. So this argument is again a scaling argument, namely you assume that at the critical point you have scale invariance, which means that the dimensionless conductance is 1 of the order of 1 whatever time. Okay, whatever the system size, whatever the time. And if on the other hand you say that dg is somehow a kind of generalized diffusion law, dl to the d minus 2, a generalized Ohm's law, and you replace the effective size of the problem by just the size of the wave packet, square root of r square, then you invert for L and you immediately find from these 2 conditions that the width square of the wave packets should scale subdiffusively. And this is also confirmed in experiment. So in other words, you have diffusion, localization, and at the critical point you have something in between, which is subdiffusion. So one remark, I recall that close to the critical point the localization length diverges, the diffusion coefficient vanishes, and this can be a problem for experiment. If you probe transport very close to the critical point, it means the dynamics is extremely slow. And experiments are always limited in time. So the first thorough description of the Anderson transition with cold atoms was performed in 2008. So at the time it was the group of Jean-Claude Garot at the Flamme Laboratory in Lille. So again, they did not use a real spatial disorder. They used this quantum kick rotor model. Actually, they use a 3-dimensional version of it, which I will not detail, but roughly it consists in modulating cleverly in time here the strength of the kick. Then you can achieve an effective 3D dynamics. And they probed here the dynamics of a cold gas, a cold atomic gas, across the critical point in momentum space, because localization is in momentum space. So the control parameter here was the strength of the kick, which is roughly KL, corresponds to KL. And here you see experimental measurements of the wave packet width, and they clearly observed the 3 dynamical regimes I mentioned before. In this experiment, they could also extract the diffusion coefficient and the localization length. And then by using a clever data analysis, which is called a finite size scaling analysis, they could extract from these measurements an estimation of the critical exponent of the Anderson transition. So this is actually an experimental estimation. They found 1.6, which is actually a pretty accurate estimation given that this is an experiment. Of course, now very shortly after this experiment with the kicked rotor, people wanted to observe 3D localization in real disordered system in 3D. So they tried, actually several groups tried, but all of them, they immediately faced the problem I mentioned before. When you have a Bose-Einstein condensate or a cold gas in general, you don't have a single energy. It's not a monochromatic wave. You have plenty of energies. So if you study transport, typically in the vicinity of the critical point, you would have classical particles, you would have localized particles, you would have critical particles. They all come together. So this means that you, in practice, you have only access to a fraction of localized particles or a fraction of diffusive particles. And if you have access to only a fraction of particles, then a detection of the mobility edge is very delicate. Nevertheless, these three groups in Palaiseau, Florence, Urbana-Champaign measured this localization fraction, and from the data they managed to extract the position of the critical point of the mobility edge. So this is as a function of the strength of the disorder. And then when people, in particular Dominique Delalande, compared this measured data to exact numerics, then people realized that all these experiments were not of the same quality. So in particular, if you look at the Urbana-Champaign experiment, you see that it's the measurements of the mobility edge is completely off. And actually, it may also give you a hint about which kind of journals you should read to have sometimes reliable data. So, so this is the end for this. So there have been further progresses in this field, but I will not talk about them here because I'm running soon out of time. So in the remaining few minutes, I would like to introduce a little bit something else, something a little bit off the beaten tracks. It's a manifestation of Anderson localization, which we have discovered recently. Although the phenomenon of Anderson localization is pretty old. So this is called the quantum boomerang effect, and this effect was measured also recently with cold atoms. So to introduce this phenomenon, let me first come back to the problem of wave packet spreading. So I recall, if you have a disordered potential, you prepare a wave packet, it will spread, and after some time it will localize due to quantum interference. But what I implicitly assume so far, all the time, is that this wave packet initially has a narrow and, more important, an isotropic momentum distribution. In other words, you prepare a cloud which has whose momenta, they have no preferred direction. All the momenta all the directions are equally likely. Okay? And a trivial observation is that if you have an isotropic momentum distribution like this, then the packet spreads symmetrically around zero. So in other words, the center of mass of the wave packet, x, here in 1D, is actually zero at all times. And now the quantum boomerang effect is a phenomenon that arises when precisely you don't start from an isotropic momentum distribution, but from an anisotropic one. So precisely you launch the wave packet in a certain direction, or you push it with a momentum in a certain direction, in a preferred direction. Okay? So before showing you the outcome for this case, I think it's instructive first to look at what is the classical expectation for this X, for this center of mass. So by classical here, I mean you describe the motion of the atoms like I presented at the outset, so by a random walk. We are in 1D, so we have two possible velocities, plus minus V0, because scattering is elastic. At each scattering event, the velocity is randomized. And then you have typically two populations of atoms with positive velocities, negative velocities, and these populations at the classical level are described by coupled Boltzmann equations. So they can be very easily solved, and by using some Ehrenfest theorem, you can immediately deduce the center of mass, the classical center of mass of the packet. It's L times 1 minus exponential minus t over tau. So it means you push the wave packet moves forward in the ballistic regime, and then it stops. It stops at one mean free path. And why does it stop? Because then momentum is randomized. Okay? So it just shifts a little bit, and that's it. Now, if you do the numerics with the Schrödinger equation, this ordered Schrödinger equation, the outcome is completely different. So this is x as a function of time, and what you find is the center of mass increases, like in the classical case, which is in green, but after some time, then it starts to goes back to zero. So in other words, the wave packet, the quantum mechanical wave packet, moves forward, and then it makes a U-turn and slowly returns to the origin point. So this is what we call the quantum boomerang effect. And now we want to understand this. So it turns out that there is a very simple proof to understand why somehow pushed wave packets go back to the origin. So I flash it here. So the idea is the following. It's based on the eigenmode expansion of your wave function. You have a wave function. You can always decompose it on the eigenmodes. But here, I choose the localized modes. Phi n are the localized mode. So then you can obtain the corresponding expansion for the density. And since the long-time dynamic is localized, the average density should be independent of time and given by the diagonal terms of the expansion. Then, if you use that your system is time reversal invariant, it's easy to show by virtue of this relation that the expansion here, in this expansion, the coefficients are actually independent of the sign of k naught. In other words, whether you push your wave packet to the left or to the right, the long-time spatial distribution is the same. And if it's the same as the distribution you would get for an isotropic momentum distribution, namely it's the Gogolin distribution, which has a zero center of mass. So we just proved, just by a decomposition of localized states, that wave packets should come back to the origin at long time, and the argument in passing is true in any dimension. Yep. It's because I know that at long time the disorder average is time independent. So if I average this, then necessarily the long time limit will be dominated just by the diagonal terms, because otherwise I will have residual time dependencies. That's the key point of the argument. Because I know that the long time limit is localized. I assume that at long time my wave packet is localized, so it no longer moves in time. No. Well, actually, you could say these phases are actually random. So when you average them, actually the dominant contribution will be given by the diagonal terms. It could as well work as an argument. Now, of course, we are in 1D. So in 1D, we can do much more, of course, than this. It's actually possible to derive an exact formula for the center of mass as a function of time. We did it using the Berezinski technique that I introduced in the beginning. So you see the result is not very enlightening, but it's relatively easy to obtain short and long time expansion for the center of mass. And what is most interesting is perhaps the long time expansion of X. You see that it decays as 1 over t squared with log corrections. So it's a very slow motion. So the dynamics of localization is fast, but the quantum boomerang effect takes some time. Here you have numerical simulation in blue compared to the exact formula in green. So the two of them coincide practically. And at long times, the red curve here is this asymptotics, which works well. In particular, by multiplying x by t squared, we are also able to identify these logarithmic corrections. So I will just in two last slides say a few words about the experimental observation of this. So the quantum boomerang effect was observed in the group of David Wells, a cold atomic group in California. Again, they use this quantum kicked rotor and not a real disordered systems. So which means that now the boomerang effect should be seen as a back and forth motion of the mean momentum and not the mean position in momentum space. And this effect actually pleased a lot the broad audience journalists, as we discovered actually after the experiment, because many of these articles popped up on the web. Even someone put a reference on Wikipedia, which is actually pretty accurate. So if you want to have a description, you can look at it. And the principle of the experiment is pretty clever, actually. So what they did is the following. They loaded a Bose-Einstein condensate in a lattice, optical lattice, in such a way that its wave function is narrow in a deep well of the lattice. And then at the beginning, they switched off this lattice, which was just used to prepare a narrow wave function. And they turned on a second lattice periodically pulsed in time. But this lattice was shifted by a spatial distance x with respect to the first one. So in this way, they really simulated a quantum kicked rotor model in which you see that the wave function has exactly the shape you would expect in momentum space if you would be dealing with a spatially disordered system. So that's exactly the counterpart in position space of the shifted momentum distribution that you need in a real disordered system. So then, with this setup in place, they just let the wave packet spread under the kicks. Then they recorded the momentum distribution and the mean momentum as a function of time, which is the number of kicks here. And apparently, you see, there are not many points, but they apparently observed this boomerang effect. What is more interesting, in my opinion, here is that they also managed to monitor the control breaking of the boomerang effect by adding stochastic noise on purpose in their system. So they're adding some noise to destroy the coherence. And when doing so, well, they found that indeed the mean position then was increasing and then saturating, which is exactly the classical prediction I showed you before. Right, so I will not talk about this, and this is just to say that you can also study it in dimension 3 across the transition, and across the transition you have the very interesting situation that you push the wave packet and the boomerang effect only exists in the localized phase and also at the critical point. But if you are diffusive, again, you push your wave packet, it stops at one mean free path, and that's it. Okay, so thank you for your attention. I also would like to point out that if you want to know more about recent developments in coherent multiple scattering of cold atoms, we have recently, a couple of years ago, written a review in Annals of Physics, and here are a couple of articles on the boomerang effect. Thank you.